An astronaut returns from space and is, provably, measurably, scientifically, younger than if they had stayed home. Not metaphorically younger. Actually younger. By real seconds that atomic clocks have counted. Time itself bent around them while they flew. And that is just where this story begins. Fact number 1. Scott Kelly aged 6 milliseconds slower than his twin brother, and they measured it with atomic clocks. NASA astronaut Scott Kelly spent 340 consecutive days aboard the International Space Station between 2015 and 2016 as part of the famous twin study. His identical twin brother, Mark Kelly, also a NASA astronaut, stayed on Earth the entire time. When Scott returned, researchers from 10 different scientific institutions analyzed everything: gene expression, gut bacteria, telomere length, cognitive performance, and timing. The conclusion? Scott had aged approximately 6 milliseconds less than Mark. 6 milliseconds sounds tiny, but here is what makes it staggering: every single one of those missing milliseconds was predicted in advance by Einstein's equations. The scientists did not discover a surprise. They confirmed a century-old prediction with living human beings. The Kelly twins are now the most important data point in the history of human time dilation research, and the full results were published in Science magazine in April 2019. Visual note: display a split-screen infographic showing Mark Kelly on Earth versus Scott Kelly aboard the ISS, with a ticking atomic clock counter showing the 6 millisecond gap accumulating over 340 days. Fact number 2. Einstein figured all of this out in 1905, before airplanes were common. Albert Einstein published his special theory of relativity in June 1905. He was 26 years old and working as a patent clerk in Bern, Switzerland. He had no laboratory, no telescope, no particle accelerator. He worked it out using pure thought experiments, what physicists call Gedanken experiments. His core insight was this: the faster you move through space, the slower you move through time. These two quantities are linked like opposite ends of a seesaw: push one up and the other comes down. He expressed this in the Lorentz factor equation, which shows exactly how much time slows at any given velocity. The incredible part? Every prediction Einstein made in 1905 has since been confirmed by real-world experiments, GPS satellites, particle accelerators, and yes, astronauts in orbit. He was working without a single piece of technology that could test his ideas, yet he got every number right. That is arguably the greatest intellectual achievement in human history. Visual note: show a timeline infographic, 1905 special relativity publication date, alongside a parallel timeline of every subsequent experimental confirmation, color-coded by decade. Fact number 3. Your GPS would be wrong by 11 kilometers every single day without time dilation corrections. This one hits differently because it is happening right now, in your pocket, on your phone. GPS satellites orbit Earth at approximately 20,200 kilometers above the surface, traveling at roughly 14,000 kilometers per hour. At that speed and altitude, two separate relativistic effects are fighting each other inside every GPS satellite. Special relativity, the speed effect, makes the satellite clocks tick about 7 microseconds slower per day than clocks on the ground. General relativity, the gravity effect, makes them tick 45 microseconds faster per day because they are farther from Earth's massive gravitational field. The net result is that satellite clocks run fast by about 38 microseconds per day relative to your phone. That sounds microscopic. But because GPS works by measuring the travel time of light signals, and light travels 300,000 kilometers per second, a 38 microsecond error compounding daily would shift your calculated position by roughly 11 kilometers every 24 hours. Engineers baked Einstein's equations directly into every GPS satellite launched since 1977. Your navigation app is, quite literally, running on relativity. Visual note: display a diagram showing GPS satellite orbit altitude, with two color-coded arrows, one for special relativity slowing, one for general relativity speeding, and a net correction calculator graphic. Fact number 4. Particles called muons prove time dilation every single second in Earth's atmosphere. Here is a fact that is essentially a live, continuous, real-time experiment happening above your head right now. Cosmic rays from deep space slam into Earth's upper atmosphere at around 15 kilometers altitude and create subatomic particles called muons. Muons are unstable, they decay and cease to exist after an average of just 2.2 microseconds. Here is the problem: even traveling at 99.7% the speed of light, a muon should only be able to cover about 660 meters before it disintegrates. Earth's surface is 15 kilometers away. By pure classical physics, essentially zero muons should ever reach the ground. Yet detectors at sea level record approximately 10,000 muons passing through every single square meter of Earth's surface every single minute. How? Time dilation. From the muon's perspective, its internal clock is running so slowly, due to its extreme velocity, that what feels like 2.2 microseconds to the muon corresponds to much longer in Earth's reference frame. The muons are surfing through dilated time all the way to your feet. This has been measured, confirmed, and reconfirmed since the 1940s. Visual note: show an animated infographic diagram, cosmic ray entry point at 15 kilometers altitude, muon decay timeline without relativity shown as a red arc stopping at 660 m, and actual muon path shown as a blue arc reaching sea level with a time dilation multiplier label. Fact number 5. Near a black hole, 1 hour could equal 7 years on Earth, and this was mathematically confirmed before we ever imaged a black hole. In Christopher Nolan's film Interstellar, the planet Miller orbits so close to the supermassive black hole Gargantua that 1 hour on its surface equals 7 years back on Earth. Most people assumed that was Hollywood exaggeration. It was not. Nolan hired theoretical physicist Kip Thorne, who would go on to win the 2017 Nobel Prize in Physics, as the film's science consultant. Thorne ran the actual calculations. For the time ratio in the film to work, the planet would need to orbit at just 1.001 times the black hole's event horizon radius, and the black hole would need to be spinning at 99.999% of the maximum possible rotation rate for a black hole. Those are extreme but physically legal conditions under general relativity. Thorne's calculations for the film were so rigorous that they actually generated 2 new peer-reviewed scientific papers about gravitational lensing published in the American Journal of Physics and Classical and Quantum Gravity in 2015. A Hollywood movie spawned real astrophysics papers. And every second of that time dilation was built on Einstein's 1915 general theory of relativity, published 100 years before those papers. Visual note: show a color-coded infographic comparing the Gargantua black hole time ratio, 1 hour equals 7 years, with a side panel listing Kip Thorne's published paper citations and dates. Fact number 6. The International Space Station moves so fast that it travels into the future by 0.007 seconds every single year. The ISS orbits Earth at 27,600 kilometers per hour, fast enough to complete a full orbit in just 92 minutes. Meaning astronauts aboard see 16 sunrises every 24 hours. At that velocity, special relativity kicks in measurably. The time dilation factor at ISS speed works out to approximately 7.2 milliseconds of time saved per year. This means that every astronaut who completes a full year aboard the ISS returns to Earth having time traveled, in a very literal, very measurable sense, approximately 0.007 seconds into their own future. By the time a 6-month crew rotation ends, each crew member is about 3.5 milliseconds younger than their Earth-based counterparts. This effect is small enough that the human body cannot feel it, but it is large enough that precision atomic clocks aboard and on the ground can detect it without ambiguity. Russian cosmonaut Gennady Padalka, who spent a cumulative 878 days in space across 5 missions, has time-traveled further into the future than any other human being in history, approximately 22 milliseconds ahead of where he would be had he stayed on Earth his entire life. Visual note: display an orbital speed infographic comparing ISS at 27,600 km per hour to a commercial jet at 900 km per hour, with a time dilation bar chart showing cumulative future travel in milliseconds per mission duration. Fact number 7. A clock at the top of a 30-story skyscraper ticks measurably faster than one at ground level. Gravity warps time on Earth right now. Here is the fact that turns everyday reality into something surreal. Einstein's general theory of relativity says that gravity warps spacetime, and the stronger the gravity, the slower time runs. This means that a clock sitting at the base of a tall building, slightly closer to Earth's massive center of gravity, ticks measurably slower than a clock at the top of that same building. This is not theoretical. In 2010, physicists at the National Institute of Standards and Technology in Boulder, Colorado, used aluminium-ion optical atomic clocks, the most precise timekeeping instruments ever built, to measure this effect across a vertical distance of just 33 centimeters. 33 centimeters. Less than the length of a school ruler. They confirmed that the lower clock ticked slower by a fraction that matched Einstein's prediction to within measurement error. Scaled up, a clock on the ground floor of the Empire State Building is measurably, genuinely slower than a clock on the 102nd floor observation deck. If you live in a basement apartment versus a penthouse your entire life, you age a billionth of a second differently. General relativity is not a space phenomenon, it is a right now, right here, on Earth phenomenon. Visual note: show a building cross-section diagram with two atomic clock icons, one at ground level, one at roof level, and a color gradient from deep blue at the base indicating slower time to bright gold at the top indicating faster time, with the 33 centimeters NIST experiment highlighted in a call-out box. Fact number 8. If you could travel at 99.99% the speed of light, you could cross the entire Milky Way galaxy in just 23 years of your personal time, while 100,000 years pass on Earth. This is the ultimate consequence of everything we have covered, and it is where time dilation stops being a laboratory curiosity and becomes something almost incomprehensible. The Milky Way galaxy is approximately 100,000 light-years across. At the speed of light, it would take, by definition, 100,000 years to cross it. But Einstein's equations show that time dilation at extreme velocities becomes so powerful that the traveler's experienced time collapses dramatically. At 99.99% the speed of light, the Lorentz factor, the mathematical multiplier from Einstein's 1905 equations, equals approximately 70.7. That means for every 70.7 years that pass on Earth, only 1 year passes for the traveler. Doing the calculation, 100,000 years divided by 70.7 equals approximately 1,414 years. Push the speed to 99.9999% of light, and the Lorentz factor jumps to 707, compressing that crossing to about 141 years of experienced time. At 99.999999%, you get that 23-year figure. Every person you ever knew would be 100,000 years dead. Human civilization would be unrecognizable or extinct. And you would step off the ship 23 years older. This is not science fiction. This is what Einstein's equations, confirmed by every experiment ever run, actually predict. Time dilation does not bend the rules of physics. Time dilation is the rules of physics. Visual note: display a galaxy-crossing infographic with a speed percentage slider, show Earth time at 100,000 years as a fixed bar, and a shrinking traveler time bar decreasing from 100,000 years at low speed down to 23 years at 99.9999999% light speed, with the Lorentz factor displayed numerically at each interval. Everything you just heard is real. Verified by atomic clocks, confirmed by living astronauts, baked into the GPS in your pocket, and published in peer-reviewed journals. Time is not the steady, reliable river we grew up thinking it was. It bends. It stretches. It moves differently for different observers depending on speed and gravity, and it has been doing this all along, whether we understood it or not. Subscribe to Moonlit Minds for daily mind-blowing facts that will change how you see the world.